Welcome to The Explainer, where we break down big topics using the source material itself. Today, we are diving into a really tough challenge, one that's super important for things like self-driving cars and public safety. How on earth does an AI keep track of every single person in a massive crowd?
Just imagine that for a second. That's the high-stakes world of what's called multi-object tracking, or MOT. This isn't just an academic problem. A tiny error can have absolutely massive consequences.
Okay, take a look at this. To us, this might just look like a chaotic jumble of people. But to an autonomous car or a sophisticated security system, every single person in there needs to be found, identified, and its path has to be predicted frame by frame, second by second.
So the big question is, how do you even begin to teach a machine to do that? To see, to remember, and to track hundreds of moving things all at the same time? Well, to get that answer, we've got to go back and look at how these tracking systems evolved, starting with a pretty simple idea, just predicting motion.
The earliest trackers, they relied on this really clever statistical tool to basically just guess where an object was going to go next.
So the first big algorithm in this space was called SORT, and it used something called the Kalman filter to follow things from one frame to the next. But, and this is a big but, it had a huge blind spot, one that became painfully obvious as soon as things got crowded.
You see, SORT only cared about motion. It was pretty good at detecting that something was there, but it was terrible at what we call association. Keeping the right name tag on the right person. So the second two people crossed paths, it would just swap their identities. That's a huge problem. So then came DeepSORT, which added a totally crucial second layer, appearance. It basically taught the tracker how to tell the difference between, say, a red jacket and a blue one. Okay, so this two-step process. First you detect, then you identify. It worked, but man, was it slow. So the next big leap forward was to try and do everything all at once. This new one-shot idea, or JD, was a real game changer. Models like Fairmont used it, and suddenly, real-time tracking was actually possible. But in that rush to be faster, it accidentally created a brand new problem, one that was really tricky, especially in crowds. It's like the AI was trying to pat its head and rub its stomach at the same time. It was trying to do these two big jobs at once, finding things and identifying them. And in really complicated scenes, it just started to buckle, confusing people who looked alike and totally losing track of them if they were even slightly hidden. And this is where a recent paper comes in. Researchers proposed this series of really targeted, clever upgrades to tackle this crowding problem head-on. And the result was a new algorithm they called CSMOT. So what did they do? First, they gave the tracker much better focus. They added this thing called a coordinate attention module, which helps the AI zero in on the exact center of an object, even in a super dense crowd. And that, as you can imagine, is absolutely critical for just getting the detection right in the first place. Second, they basically made the AI a better judge of character. They used a new training technique called angle center loss. Think of it like a really tough training exercise that forces the AI to focus on the tiniest little details that make each person unique. This dramatically cut down on the confusion between people who looked similar. And finally, they completely changed the tracking strategy. See, older models, if they weren't sure about someone because they were blocked from view, they'd just ignore them. But CSMOT, it says, nope, let's try to track everything, even the low-confidence sightings. And this one change dramatically reduced the number of times a person's track got broken. Okay, now this is where it gets really cool. Just look at this direct comparison on the screen. On the right, you've got the new approach, CSMOT. See how it manages to keep a consistent track on people even when they're almost completely hidden? Now, look at the older model on the left. It gets confused, it swaps their IDs, it's just a mess. The difference is night and day. And the numbers, well, they tell a really powerful story. Compared to its baseline, CMS-Olin cut down on those identity switches by almost 12% on one benchmark, and then a whopping 34% on a more crowded, difficult one. Now, a 34% reduction in errors like this, that isn't just a number on a chart. In the world of autonomous driving, that could literally be the difference between a safe trip and a terrible accident. So CSMOT is clearly better, right? But how much better? And how do researchers even measure what better means in the first place? It's actually not about one single number. It's all about finding the right balance.
Remember those two big jobs, detection and association? Well, that's what these key metrics are all about. For a long time, the two main scores were MOTA, which is all about good detection, and IDF-1, which is all about consistent identification. But the new gold standard is HOTA, and it was created to give a much more balanced, complete picture of how well a tracker is really performing.
And this chart is where CSMOT really shines. It's not just good at one thing. It's a true all-arounder. The goal here is to be as far to the top right as possible, and just look where CSMOT is. It's pushing the boundaries on detection, on identity consistency, and on that combined HOTA score. It's basically a new benchmark for what's possible.
But here's the thing. Accuracy is only half the battle. Because for something like autonomous driving, a tracker doesn't just have to be good. It has to be incredibly, unbelievably fast.
Out there on the road, a self-driving car doesn't have the luxury of hitting a pause button on the world so it can think. That tracking algorithm has to process an absolute fire hose of sensor data, and it has to do it in the blink of an eye. And that is why getting the hardware and software to work together perfectly is so critical. Get this, one study found that running these algorithms on a specialized GPU could make them over 7 times faster than on a really good multi-core CPU. That is just a massive leap in performance. So, what does this all mean? It means we are right on the cusp of having AI that can see and understand the world with the kind of reliability we absolutely need for these life-or-death applications, like, getting you home safely in a self-driving car.
So let's just recap the journey here. We've seen how trackers evolved from only looking at simple motion to becoming way faster with these one-shot models, and now how researchers are solving those final tough hurdles of crowding and occlusion with these incredibly clever, targeted solutions.
And that's our explainer for today. We've come a really long way from the days of an AI forgetting a pedestrian at a crosswalk. As these systems get better and more reliable, the question is no longer if we can trust them, but how we're going to integrate them into all of our lives.